Unveiling the Cosmos, Transformative Astronomy Breakthroughs in September 2025. A Golden Age of Cosmic Revelation. In the ever-expanding tapestry of human knowledge, September 2025 stands as a pivotal month for astronomy, a discipline that bridges the infinitesimal scales of quantum ripples in spacetime to the colossal architectures of planetary nurseries light-years away. The James Webb Space Telescope, JWST, humanity's most advanced orbital observatory, continues to dominate headlines with its infrared gaze piercing the veil of dust and distance. Launched in December 2021, JWST has already rewritten chapters on the early universe, exoplanets, and star formation. This month alone, it delivered 2 seismic discoveries in planet formation that challenge foundational models of how worlds like ours come to be. Complementing these, ground and space-based observations illuminated Martian auroras, unveiled a shadowy trans-Neptunian behemoth, and celebrated a decade of gravitational wave detections that affirm Einstein's century-old predictions. These breakthroughs are not isolated fireworks but interconnected threads in the narrative of cosmic evolution, blending cutting-edge technology with theoretical physics to reshape our understanding of the solar system and beyond. This video delves deeply into these developments, weaving in historical context, scientific methodologies, broader implications, and illustrative examples. From the dusty disks birthing gas giants to the ethereal glows dancing over Martian dunes, and from the warped fabric of spacetime to the frozen fringes of our solar system, September 2025 reminds us that the universe is not a static museum but a dynamic laboratory, revealing secrets at a pace that outstrips our wildest imaginations. JWST's window into planet formation, WISPIT-2b and the birth of worlds. At the heart of September's astronomical fervor lies JWST's unprecedented direct imaging of a protoplanet in mid-formation, announced on September 15, 2025. Dubbed WISPIT-2b, short for Webb Imaging of Substellar Protoplanetary Intricacies, this nascent world orbits a young sun-like star approximately 430 light-years from Earth in the constellation of Lupus. Captured in exquisite detail on August 27, 2025, during a 5-year observational campaign led by an international team from the European Southern Observatory, ESO, and NASA's Goddard Space Flight Center, the image shows Wispit-2b as a glowing ember amid a multi-ringed protoplanetary disk, a swirling vortex of gas and dust that serves as the cosmic cradle for planetary systems. What makes this discovery revolutionary? For decades, astronomers have inferred planet formation through indirect methods, spectral signatures of accreting material, gaps in circumstellar disks observed by telescopes like the Atacama Large Millimeter, Submillimeter Array, ALMA, or the occasional silhouette of a mature exoplanet transiting its star. The core model, known as core accretion, posits that planets coalesce from microscopic dust grains clumping into pebbles, boulders, and eventually kilometer-sized planetesimals over millions of years, a process too slow and obscured to witness directly. Wispit-2b appends this by providing the first visual snapshot of active accretion. The planet, estimated at just 5 million years old and roughly the mass of Jupiter, appears as a bright, heat-radiating orb carving a gap in the disk, voraciously gobbling gas and dust like a cosmic vacuum. Its glow, primarily from gravitational contraction and residual formation heat, peaks in the infrared spectrum, where JWST's mid-infrared instrument, MIR, excels, revealing intricate details invisible to shorter wavelength telescopes. To appreciate the challenge, consider the scale. WISPIT-2b's host star, a Tauri-type pre-main sequence star analogous to our Sun 4.6 billion years ago, bathes the disk in ultraviolet radiation that would overwhelm optical imagers. JWST's sunshield and segmented mirror, spanning 6.5 meters, allow it to peer through this chaos with a resolution 100 times sharper than Hubble in the near-infrared. The image, a composite of MIR and near-infrared camera, NIRCAM, data, depicts concentric rings, likely sculpted by resonances from unseen siblings, echoing the debris disk around HL Tauri, famously imaged by ALMA in 2014 but lacking a confirmed protoplanet. The implications ripple outward. This baby planet challenges pebble accretion models by suggesting faster growth rates, potentially driven by magnetic fields or turbulent disk dynamics. If validated, it could explain the prevalence of hot Jupiters, massive worlds hugging their stars, in exoplanet surveys like Kepler and TESS. For astrobiology, it raises tantalizing questions. Does WISPIT-2b's rapid formation preclude rocky inner planets, or might outer giants shepherd volatiles inward, as theorized in the Grand Tack hypothesis for our own solar system? Early simulations, run on supercomputers at NASA's Ames Research Center, indicate WISPIT-2b could migrate inward, disrupting potential Earth analogs. A sobering reminder that our habitable oasis might be the exception, not the rule. A carbon-rich enigma, rethinking the chemistry of rocky worlds. Barely 2 weeks prior, on August 31, 2025, JWST unveiled another bombshell. A planet-forming disk orbiting a distant star, brimming with carbon dioxide, CO, yet strikingly barren of water vapor. Located around a young star in the Orion Arm, roughly 1,000 light-years away, this disk, catalogued as PDS-70C's companion structure, defies the water-dominated chemistry assumed in standard models of terrestrial planet formation. Detected via JWST's NIR spectrometer, the observations reveal carbon dioxide abundances up to 10 times higher than expected, with nary a trace of hydrogen oxide in the midplane where rocky cores would aggregate. Historically, planet formation theories, from the nebular hypothesis of Immanuel Kant and Pierre-Simon Laplace in the 18th century to modern variants like the NICE model, hinge on water ice as a scaffold. In the solar nebula, the snowline, beyond which temperatures drop below 150 K, allowed water to freeze, facilitating rapid planetesimal growth and delivering volatiles to inner worlds via comet impacts. Earth's oceans, for instance, are thought to stem from such deliveries, estimated at 10 to the power of 21 kg of water from carbonaceous chondrites. This new disk, however, suggests carbon chemistry dominates in some environments, possibly due to elevated stellar metallicity or asymmetric irradiation from a binary companion. The data, spanning 20 hours of integration time, show carbon dioxide sublimating directly from dust grains, bypassing water's role and potentially yielding dry, carbon planets. Worlds with diamond rains or supercritical carbon dioxide atmospheres, akin to Venus but primordial. Examples abound in exoplanet catalogs. LHS 1140b, a super-Earth 49 light-years away detected by TESS in 2017, exhibits a carbon dioxide-heavy atmosphere per JWST follow-up in 2024, hinting at similar origins. Implications for habitability are profound. Without water, these planets might host exotic biospheres reliant on carbon solvents, or none at all, narrowing the search for life to wet disks like TW Hydrae, where JWST confirmed water megamasers in 2023. This discovery, published in Nature Astronomy on September 1, 2025, spurred immediate modeling revisions. Teams at Penn State University, using the Gadget 4 code, simulated disk evolution with variable CO ratios, predicting 20% of systems might birth carbon-rich terrestrials, up from negligible odds. It also bolsters the case for JWST's extended mission, approved through 2030, emphasizing time-of-flight mass spectrometry for volatile mapping. Martian auroras, forecasting the red planet's emerald dance. Shifting from stellar nurseries to our cosmic neighbor, September 12, 2025, marked a milestone in planetary science. NASA's Perseverance rover captured visible auroras on Mars for the second time, igniting hopes for predictive models to safeguard future colonists. Unlike Earth's magnetosphere-shielded polar lights, Mars auroras, proton auroras, technically, stem from solar wind particles slamming into the thin exosphere, exciting oxygen atoms to emit green light at 557.7 nanometers. The first sighting, in March 2024 during a G5-class solar storm, was imaged by Perseverance's Mastcam-Z, revealing diffuse glows over Jezero crater. This second event, triggered by a coronal mass ejection, CME, on September 8, was fortuitously timed during Perseverance's Sol 1200 milestone. The rover's SuperCam instrument, equipped with a laser-induced breakdown spectrometer, not only photographed the aurora but analyzed atmospheric composition, detecting elevated ionized oxygen. Presented at the European Planetary Science Congress on September 10, the data enabled a machine learning forecast model, trained on MAVEN orbiter archives since 2014. With 85% accuracy, it predicts auroral intensity from solar wind speed and interplanetary magnetic field orientation, crucial for Artemis-era missions where radiation spikes could dose astronauts with 110 millisieverts per event, equivalent to a year's background radiation on Earth. Contextually, Mars' lack of a global magnetic field, lost 4 billion years ago, exposes it to chronic solar erosion, stripping 100 grams per second of atmosphere. Auroras map these interactions, revealing flux ropes in the induced magnetosphere. Analogous to Jupiter's auroral ovals, Martian displays are global but faint, visible only during storms. For example, the 2018 MAVEN detection during a Carrington-level event illuminated half the hemisphere. This breakthrough, led by the University of Leicester, underscores interdisciplinary synergy. Plasma physics meets rover engineering, paving the way for in situ forecasting via CubeSat constellations proposed for Mars sample return. The Shadowy Giant, 2017 COVALENTO1F201 and the Solar System's Fringe. On September 6, 2025, astronomers at Princeton University announced the confirmation of 2017 COVALENTO1F201, a massive trans-Neptunian object, TNO, lurking at the Solar System's ragged edge, potentially qualifying as the fifth dwarf planet. Initially flagged in archival dark energy survey data from 2017, this 700 km wide icy relic boasts an eccentric orbit spanning 80 to 1,500 astronomical units, a 25,000-year pilgrimage that defies clustering patterns in the Kuiper Belt. Discovered via adaptive optics at the Magellan Telescope, 2017 OF201's reddish spectrum suggests a methane-ethane ices coating, akin to Pluto's albedos. Its isolation hints at shepherding by an undiscovered Planet 9, a 510 Earth mass world posited by Caltech's Mike Brown in 2016 to explain TNO alignments. Historical parallels include Eris, 2005, which demoted Pluto, and Sedna, 2003, whose 11,400-year orbit expanded the Kuiper Belt's definition. Vera Rubin Observatory's 2025 Legacy Survey of Space and Time, LSST, will hunt siblings, but 2017 COVALENTO1F201 already reshapes dynamical models, suggesting a more chaotic outer solar system sculpted by early giant migrations. Implications extend to origin stories. Did it form in situ or scatter from a disrupted inner disk? Isotopic studies, via JWST's planned 2026 observation, could trace volatiles to the interstellar medium, informing comet compositions like 67P Churyumov-Gerasimenko, sampled by Rosetta in 2014. Ripples in spacetime, the gravitational wave decade and GW250114. Crowning September's triumphs, the 10th anniversary of the first gravitational wave detection on September 14, 2015, GW150914, from merging black holes 1.3 billion light-years away, coincided with analysis of GW250114, a January 14, 2025, signal verifying Stephen Hawking's area theorem. Detected by Ligo-Virgo-Kagra, LVK, this binary neutron star merger at 200 million light-years released energy equivalent to 10 solar masses, its chirp signal matching general relativity to parts per million. Einstein predicted gravitational waves in 1916 as spacetime distortions propagating at light speed, but detection eluded until LIGO's 2010 upgrade. GW150914, announced in 2016, earned the 2017 Nobel Prize and birthed multi-messenger astronomy, fusing waves with electromagnetic counterparts like GW170817's kilonova. GW250114's import, Hawking's 1971 theorem states black hole event horizons never decrease in area, a quantum corollary to the second law of thermodynamics. The signal's post-merger ringdown, damped oscillations, precisely matches Kerr metric predictions, ruling out area shrinkage and bolstering holography in quantum gravity. Over 10 years, LVK logged 200+ events, from primordial black hole hints to intermediate mass mergers challenging stellar evolution. Examples include GW190521's 150 solar mass behemoth, suggesting hierarchical mergers in dense clusters. Future upgrades, like LIGO India, 2026, and the Einstein Telescope, 2030s, promise 1,000 detections yearly, probing cosmic inflation and dark energy. As X posts from the anniversary reflect, from @ego_Virgo's celebratory video to @OzGravityGuru's journal shoutout, the community pulses with excitement. Broader horizons, echoes and extensions. These breakthroughs echo wider September currents, JWSTs, little red dots, enigmatic early universe objects possibly hosting supermassive black holes, challenging reionization timelines. ESA's detection of a stellar jet in the Milky Way's outskirts unveils star formation's fury, while NORLAB's silane in a brown dwarf atmosphere hints at prebiotic chemistry. Skywatchers note Saturn's opposition on September 21st, framing these discoveries against autumnal splendor. Conclusion: toward an infinite frontier. September 2025's Astronomy Odyssey, from WISPIT-2b's fiery birth to GW250114's spacetime symphony, affirms our era as one of profound revelation. These advances, born of global collaboration and technological audacity, not only refine theories but inspire. What if carbon worlds team with silicon life? Might Martian auroras herald shielded habitats? As JWST's gaze deepens and LIGO's ears sharpen, we edge closer to answering whether we're alone, or merely the prelude to a grander chorus. The cosmos, once inscrutable, now whispers secrets. It falls to us to listen, learn, and launch onward.